Okay, so how is everyone today? Good? Yeah? Good. Okay, good. Fine. So what we were talking about last time, just as a brief review, is that, we talked about sets. And primarily, the main kind of sets that we were interested in, so primarily intervals. And combinations of intervals. Specifically, what we said is that given an interval or two intervals, we can calculate a new set with the following kinds of operations. We can do complement. So we could say, what's the complement of a set? So what is the complement of a set? Yeah, the opposite. It's everything that's not in the set. Okay. Then, an example would be something like, for this would be something like, we could write down the interval 2 to 6, say, like that. And we could draw it. 2 to 6 would look like this. And then we could write 2 to 6 complement. So the notation for complement is superscript C, like that. And then that means everything that's not in the set. So in the case of shading or coloring, that means that now we're going to color all the points that aren't colored up there. So again, we'd have to single out 2 and 6. And then, we have to do, for this one, we have to do the opposite. So because that one is filled in, that one's not filled in. And because this one is not filled in, that one should be filled in, right? So it's there. And now, because all these points are colored, none of these points are colored. And because, and opposite on the other bits. So like this. So we have complement. And similarly, we've got union and intersection. Okay, so, we did that. Now the primary context for us of one is at this point is domain of expressions. In the following kind of sense, we can have an exercise like find the domain of the square root of 2x plus 9. Well, in the end, at this point in the class, for the expressions that we use, there's just two kinds of ways where something can go wrong. Well, because a domain was not given, that means that the domain of this expression is the natural domain, and natural domain is the largest set of x's for which the expression is defined. So, in some sense, we need to know when can this be defined, and the answer is that because this is an even radical, the input, the argument to the radical, has to be greater than or equal to 0. Okay, so we could do a brief calculation, which basically comes down to we need to solve 2x plus 9 greater than or equal to 0. So that's 2x is greater than or equal to -9. So that's x is greater than or equal to -4.5. So as a result, we could say, therefore, the domain is -4.5 to infinity, something like that. And then we had other examples where the domain was the union of some intervals. So this interval, union that interval, blah, blah. Okay. Now, domain is the set of all possible inputs So it's the inputs. And so like considering, say, the vending machine that's right over there, you can put money in it. That's the kind of stuff that you put in it. And then, candy comes out. All right. So the domain of the vending machine is, U.S. currency. And then the stuff that comes out is candy. But we need a math name for the stuff that comes out. All right. So domain is the set of all possible inputs, and the codomain is the set of all possible outputs. So we're not going to do it today, but in the coming lectures, the question is it's not going to be just like this. It's not going to be just find the domain of this. It's going to say find the domain and the codomain of this. Okay, so then it'll be okay. Well, first we have to calculate the domain. Then once you have that right, then you can go on to calculate the codomain. So sometimes I'll give you an expression and I'll give you the domain. So I've explicitly given to you. So here's the expression, and the domain is thus. And then the only question on such an exercise would be, okay, find the codomain. But we're going to end up being interested in both. But for now, finding codomain, that's just an issue of foreshadowing. So now, concerning this expression, say, so to give an example. If the expression is that, uh, 2x plus 9, then here's how we're going to sort of reckon it. So we'll say, okay, we're going to consider this expression to be like a machine. So it's a machine, like a vending machine. And if you use input 0, you put 0 in for the variable, then what comes out? 3. 3 will come out. Because what the requested work is that, okay, take that expression, everywhere you see x, replace it with 0, and then carry out the arithmetic. So 2 multiplied by 0 plus 9, well, that'd be 9, and then the square root of 9 is 3. So what I'm saying is that this input of 0 produces this output of 3. That input, that output. Similarly, if we plug in, say, I don't know, 5 into the machine, then what comes out? almost square root of 19, right? So that's just some number. So we're going to be wanting to keep track. This input, that output. This input, that output. So we're going to be keeping track of two things, a pair of numbers. So we want to keep track of input-output pairs. And, you know, the way we're going to write it down, of course, this is real clumsy to write that. That's so much writing. So the way that we're going to write it down compactly is like this. So we'll say that input 0, output 3, we'll write that down as 0, 3, like that. And then input 5, output 19, square root 19, we'll write that down as 5 square root 19, like that. Input, output. Okay, and so what we need is we need to build up all the language and notation and everything so that we can all use this quickly and efficiently. So there's a lot of little details to get worked out. So that's what we're going to work out today. Okay, so in the end, like for this, we were basically up until the end of last lecture, we were in some sense only interested in the inputs. But now we're going to be interested in the outputs also. Okay. So before we get to that, we need to have a slight digression about history, because otherwise the next page, well, this will make the next page make more sense. So this is just a historical digression about left and right. So, all right, we have two hands, a left hand and a right hand. And it's really pretty arbitrary, what we ended up calling, this side and what we ended up calling that side. It's an arbitrary name, but we need a name so that we can distinguish between them. It's arbitrary in the sense that, for example, right is not the same word in every language. Okay, in English it's right. In what is it in Spanish? Yeah, that one. And then in English left, and I know the one for left in Spanish. I think it's izquierda. Okay, so the names are arbitrary. Fine, but in the first place, about 90% of humans are right-handed. Okay, not moralizing. I'm just saying that that's approximately true. So there's a lot more right-handed folks than left-handed folks, and so left-handed folks end up having all kinds of issues because the world is sort of skewed towards favoring right-handed people. So it's totally a common story if you're left-handed or if you have a left-handed family member, child, whatever, that they're always suffering through having to use right-handed scissors. Because, if 90% of everyone is right-handed and you manufacture scissors and you have to make a choice, like, you're going to make right-handed scissors. Okay, and then doors very often are, skewed towards being slightly more friendly to right-handedness and all this kind of stuff. And so the world in some sense favors right-handed people. For no reason other than it's just a historical contingency that most people are right-handed. So here I have an interesting question for you. So there are in fact some folks who can more or less equivalently use either hand. And what's the name for those people? Ambidextrous. Ambidextrous. Okay, but now in Latin, there's a Latin word for left, and there's a Latin word for right. And I'm going to leave myself a place to write that. So now we have the word ambidextrous. Of course, that means able to use both hands. Okay, that's neat. And then now here's another one. Is that what is the opposite? I'm going to leave myself some room to write this. So I'm going to leave myself a blank. So here's a blank right here. And here's a blank right here. So opposite of wrong. I'll leave myself a blank right there. And then I'll write one more, and then I'll write something like this. So like you're reading like a suspense novel or a scary novel, you could say something like the bad guy had a blank plot or scheme. Okay, so now I'm going to start filling these in. So there's plenty of ways you could fill this one in. You could just say bad again. The bad guy had a bad scheme, but that's kind of a clumsy sentence. So I'm going to write the bad guy had a sinister scheme. That's a good word. It means bad. Sinister. Ooh. What's the opposite of wrong? Right. Which is curious because the opposite of right, as far as handedness, is left. Okay. So ambidextrous. That's interesting. So what is the Latin word for left? The Latin word for left is sinister. That's because historically speaking, in not too many centuries ago, people who were left-handed were considered to be evil.
My brother's left-handed.
Yeah, makes perfect sense. And ambidextrous means being able to use both hands, like equally well. I can use scissors with both hands or whatever. What's the Latin word for right? So what does ambidextrous mean? In a literal sense?
Able to use two rights.
It means that when you're referring to hands, it sort of literally means you have two right hands. So your left hand is as good as a right hand, in some sense. So the opposite of wrong is right, and a bad guy has a sinister scheme. Sinister just means left. That's all that it means. In the end, the reason for this, all this historical baggage in our language concerning left and right, just has nothing more to do with than folks superstitiously used to believe that left-handed people were, evil or disturbed or whatever. And it's not even that old because actually I'm left-handed, but I write with my right hand because my kindergartner teacher made me use my right hand. But I do everything else with my left hand. Okay. Fine. So that being said, now we're going to continue the historical process of of preferring right-handedness to left-handedness. Okay. So this one will be called R1 and R2. And we're going to do it in 2 columns. And on the left column, we're going to write stuff that you already know and a little bit of new. And then the right column is going to be more or less completely new. So concerning R1, when you plot it, when you draw it, so plot looks like a horizontal line. Now, before today, we would draw it like this. You know, that's how we draw it, and we might shade some intervals on it, you know, more or less just like we have there. But we're not going to do that anymore. So from now on, well, okay, before today we might draw it like this, or you know, something like this, you know, this kind of thing, etc. Okay, so from now on, we will draw them like this. So if we want to draw the whole real line, we'll draw it like this. And then now, so far the difference between these two is that you know, this one has its barbs on the right side, so they both have right barbs. These little hook thingies are called barbs. But so far I haven't drawn anything right there. So before today, the meaning of those barbs meant that it keeps going to the right. You know, it just goes all the way that way. And those barbs mean it's going all the way that way. And then the meaning of that symbol means that it stops there, and moreover, that point is not present. So it doesn't go any further to the left, and that point isn't there. And so, you know, we made our whole, you know, nice convention of various stuff. Okay. So now, when we want to say it continues going all the way to the left, we're going to draw barbs, but they're going to be pointing weirdly. That's how we're going to draw it. So it's the barbs are still there, but they're pointing in the same way as that one. So it's the same. Like that. So we can still draw this one. And we can still draw this one. But, you know, this is going to be the same as this one. Meaning that we put a little barb in it, like that. So those are now the same. Okay, and that's the opposite of this, but with the barbs going the other way. All right, so now here's the deal. We have the right-handed rule. The right-hand rule is that on the real line, when you're drawing it, the increasing direction is to the right. So, and that's indicated in any case by the direction of those barbs. So this one is drawn that way. So in any case, the barbs, or hooks, whatever you want to call them, indicate the increasing direction. So, for example, this one, and this one, these are both the whole real line. So, this one right here, the one on the top, it goes, all the way to the left, and it also goes all the way to the right. And this one also goes all the way to the left and all the way to the right. But notice that the barbs are opposite. So this one increases in what direction? To the left. So this one increases to the left. And this one increases to the right. Okay. Then now for these little intervals, we're going to be able to say, is this interval a positive interval or a negative interval? And in the end, that's going to be called sine. Sine indicates agreement with the world. Agreement. So here's what I mean, is that if the world is drawn in the standard way, to the right, then I could draw a little interval. So, for example, here's a little interval, so something like this. So I'm going to draw it just slightly above, but only so you can see it. So here's a little interval. Okay, and I haven't drawn a barb, so now I'm going to draw a barb, and I'm going to draw it like this. So is that one in agreement with the world? No, it's the opposite of the world, right? It's sort of like swimming upstream. It's going the other way. So this is going to be negative. Okay, whereas this one, like that. So does it have the same sense or the opposite sense of the world? The same, right? So this one's going to be positive. And it doesn't matter where they're located, like left and right. The only thing that matters is that barb. So, if I continue this, way over here and draw another interval, like this one, would this one positive or negative? Positive, because it's going the same way as the world. So it doesn't matter where it's located. All that matters is that barb. All right. That's curious. So now let's start talking about the corresponding things over here. So, positive and negative just indicates agreement or disagreement with the world. And then the right-handed convention is that basically any time that we have a choice, we're going to say that the increasing direction is to the right, unless there's like real good reason to do it the other way. Okay. For R2. What this means is the 2 in the end is going to mean that we want to keep track of two things, two-dimensional objects. So the way that we're going to do this is and deal with it is that we're going to have a plot, but now the plot looks like a plane. Okay, so then the way that we're going to do it is we're going to draw two copies of R1. And we're going to draw two copies of R1, so two of those, two of those, and it's going to look like this. So here's the first one. So we're going to make these so these two copies, they're going to be at right angles, like this, so right angles. So since we already know how to draw one copy, and because we have the right-handed rule, I'm going to draw a horizontal one. And because it's horizontal and we have the horizontal, we have the right-handed rule, I'm going to go ahead and, you know, make it in agreement with that rule. And now I need another axis, and because we're going to do it at right angles, so we're going to have another axis like this, and this is a right angle. And so now here's the deal, is that from what we've currently drawn, we haven't indicated if the increase, where the vertical axis is concerned, is the increasing direction up or down. So it's going to end up being up. So I know that many of you have seen all this before. But the reason why the increasing direction is up is not because Ms. Harris said so. I mean, I'm sure she did say so. But that's not the reason why. The reason why, in the end, is because we want to have a right-handed rule. A rule. Why should it be this way? It's not arbitrary. There's a reason. Okay. So, you know, this one-dimensional thing, this is a right-handed arrow. It's a right-handed arrow because it increases to the right. And that one's a left-handed arrow because it increases to the left. This is a one-dimensional thing in the sense that, you know, if you're standing right there at that point, and that's the whole world, just that arrow, meaning that you can't leave it. You can't go up and down. You can only go this way. Then there's only one direction you can travel. So this is a one-dimensional thing. A two-dimensional thing is like this sheet of paper. Where you are, you can go, you know, up, down, left, right. You can do all that. Okay. So this is a you know, a left-handed arrow, a right-handed arrow. So now what we want is, how are we going to indicate left-handedness in the two-dimensional sense and right-handedness in the two-dimensional sense? Okay, so here we are. So so two-dimensional, left-handed, and two-dimensional, right-handed. So here's the idea. Here's the idea. Is that notice that if you take your hands and you hold your thumbs out, you know, hold them out, notice that in both cases your fingers, of course, curl towards your palms, not away from your palms, right? They don't do that. They do this. Okay. So then, if you put your left hand on the page and hold your thumb up, then your fingers curl like this. They, you know, from your thumb, they're going in the clockwise direction. Okay. So left-handed is going to be a swirl that is clockwise. So those are like your fingers in your left hand. Okay, and then what's right hand going to be? A swirl, but going counterclockwise. Can you see it? So now, so this is clockwise. This one counterclockwise. And now what we want to do is just like we have a in this case, this is like a little one-dimensional piece of the world. So the world is the line, and there's a little one-dimensional piece. So now the world is this plane, and we want a little two-dimensional piece. And there's lots of different two-dimensional objects like circles and triangles and things like that. Those are all two-dimensional bits. You know, any shape that you can cut out with scissors, any shape that you want. So to make our lives as simple as possible, and to also deal with the fact that these are at right angles, I'm going to choose a shape that has all right angles. I'm going to choose a rectangle. Okay, and to make it even easier, I'm going to choose a square. So here's the rule: is that we're going to draw a square. And we're going to draw it on both sides. And you know, the outline is going to be like this. But now we're going to have those dots are just there for you to see where we're going to draw. I haven't drawn it yet. So here's going to be the rule of how we're going to draw it. So this, you know, this is the one-dimensional case, this is the two-dimensional case. The two-dimensional case is that we have two copies of the line. This one is the first axis. It's the first axis because in the end, we already said what we were going to do if we just had one axis. So if we have two axes, first we're going to start with that, and now we're going to have this one. So this one is the second axis. And here's the way that we're going to draw the square. Is that notice that the square, some of its sides are parallel to the first axis, and the other sides are parallel to the second axis. So in this case, for the left-handed situation, we're going to follow the second axis first. We're going to follow the second axis. So from here, we're going to follow the second axis and go up. Okay, so we're going to go like that. And then from here, we're gonna go in agreement with the world. We're going to go to the right. And now notice that if you had a cup of coffee and you put your creamer in it or whatever, and then you put your spoon right there and you started stirring it, how would it swirl? Like that. Okay. Whereas, if from the same starting point, if we follow the first axis first, then we would go this way. And now let's follow the second axis. We'd go this way, and then complete the procedure. And again, if we were stirring a cup of coffee, which way would it be swirling? Like that, in a counterclockwise direction. Okay, so what we want is we want to have this rule, is that we want it to be the case that when we take a square, any square that we want, so you pick out a square, and we want to have the following idea, that from here we should follow the first axis for a little bit, and then follow the second axis, and the result should be right-handed instead of left-handed. So so if that's the starting point, then which direction is the first axis pointing? That way. So that means that from here we've got to go this way. And in some sense, if we ignore the dottedness from there, we now are going to decide, we know that we want counterclockwise swirl, so what needs to be the vertical increasing direction? Is it going to be up or down? It's going to have to be up. Why up? Right, because if we went down, then it'd be going like this. That'd be left-handed. Wouldn't be right-handed. So as a result, the increasing direction is up. So drawing these in this way, oops, I didn't mean to do that. So, you know, for this one, the right-handed system is like this. So increasing direction is in the first axis is to the right, and in the second axis is up. And a left-handed system is the increasing direction is to the right, and the horizontal increasing direction is to the right, and the vertical increasing direction is down. In the end, the reason is that, you know, over here, if you want to draw, you choose any point you care to start at. So right there. And then follow the first axis. We follow it. And now follow the second axis. We follow it. And then finish out the job, finish out the square. Well, that's going to make a clockwise swirl, left-handed swirl. Whereas over here, you select any point you care to start at. So here, first follow the first axis, then follow the second axis. Well, then now the swirl is counterclockwise. Okay, so left and right-handed. Okay, then now negative and positive is just whether or not you happen to be in agreement with the world. So that's all that it means. So, for example, down here, you know, the swirl of this world looks like this. So first to the right and then down, so like this. So that's how it's indicated. And then I could draw like a nice, say, triangle. That's a two-dimensional shape. That's a little two-dimensional part of the world. And then what if I put this on it? So then the question becomes, is that a negative triangle or a positive triangle? It's a negative triangle. But wait, I thought we said that it's right-handed, right? That ignoring all the rest of it, that triangle is right-handed because the barbs are, you know, going like that. So this is a right-handed triangle, but you're telling me that it's actually negative? Why is it negative? Because it's in a left-handed world. It's in the opposite. Right. So this one, you know, a world where everybody uses 90% of everybody is left-handed, and then here we have a right-handed triangle looking for some scissors, right? Okay. Similarly, if we take this this same triangle and transport it over to here, it's still a right-handed triangle, but now it's a positive triangle because it's in agreement with the world. So can you see it? All right. Any questions about this? Left-handed and right-handed. Okay. So you know, this convention continues is into any number of dimensions that you care to take it. For example, in 3 dimensions, you know, like this room that we're in, you know, there's wires up in the ceiling. They carry electricity. And if we had a wire running from this wall to that wall, and it had DC current, which just means that the current is always pointing in the same direction as time goes. It's not flipping back and forth. So if there was a DC current flowing from that wall to that wall, like that, so it's going that way. And if I used my right hand and pointed my thumb in the direction of the current, then the existence of that current, that electric field, that's going to cause a magnetic field to come into existence, and it's going to be swirling around that wire. That's why motors and things work. What's going to be the direction of the swirl of the magnetic field? The direction of my fingers. So it's going to, so if it's pointing to that way, the magnetic field is going to be going around it like this, because that's how my right hand fingers go. Again, that's just right-handed rule. All right, good. Another place where it comes up is when you want to in chemistry. So if you end up taking, say, organic chemistry, you are going to have to look at various carbon atoms and say, well, is this going to be, according to the convention in chemistry, is this going to be a left-handed carbon or a right-handed carbon? So, like when you hear a chemistry name, like say something like dextrose. Well, dextrose is a kind of sugar, and in the end, it's called dextrose because it has something to do with it with right-handedness. Dextrose is a sugar, and it has a mirror reflection, and I don't know the name of its mirror reflection unless it's called like synacrose or something like that. I don't know, but so that's all over chemistry. Okay, fine. So next. So this is a continuation of that page. So in the R1 case, the 0 cuts the line into two parts. So if we draw our line, and if we indicate where 0 is, then there's a left part and a right part. So it just cuts it. But now we want to have names for that, and we can't say left and right because it has to work even if the barbs are pointing the other way. So we have to have some kind of rule. So if we get out a ruler, which is to say a linear measuring device, get out a ruler, and I measure the distance from 0 to that point. Suppose that the ruler says 3. Well, there's another point that also is distance 3 to 0. This point is also distance 3. But we can't call them both 3. They can't both be 3. One of them's got to be positive 3 and one of them's got to be negative 3. But how are we going to make that decision? Of course, we all know that that one's going to be positive 3 and that one negative, but why? In the end, it has to do with, it's not the right-handedness anymore. Rather, it's going to be agreement or disagreement with the world. So here's the deal, is that if we make a little interval, and we draw from 0 to the point in question. So starting at 0. So we make a little interval starting here, and then we go over to that 3. Then what direction was I drawing? Well, I was drawing that way. So I'm going to indicate that I was doing that with this barb. So now is that barb in agreement or in disagreement with the world? Agreement. So that agreement means that this one is positive 3. And then, for this one, if we start at 0 and then go over to that 3, so starting at 0 and then to that one, now the barb is pointing that way. So is that in agreement or disagreement with the world? Disagreement, which means that this is negative 3. Now, entirely analogously, if we do this, and say that this is 0, and I say, and we measure the distance from 0 to this point. So that distance is 5, but what's the name of that point? That's negative 5. Why is it negative 5? Yeah. because, you know, if you were to draw it from 0 to that point, then the barb is like that, which is in disagreement with the world. So that's -5. Okay. So we'll just mention this because we just have 30 seconds left. When we want to draw the plane, now instead of the world being cut into two pieces, negative and positive, now the world's going to be cut into 4 pieces, because what we're going to do is we're going to arrange it to where the zeros of both axes are right there. So they're both right there. And we're going to call that the origin. Origin just meaning that that's where you start. So that just like this. Okay. Then these are going to be cut into 4 pieces, and we're going to end up naming them quadrants, 1 through 4. So if this one is called quadrant 1 and it's written in Roman numerals, then I have a question. Which one should be the second quadrant, and why? So, you know, the second quadrant's got to be either that one or that one. It wouldn't make sense, it seems to me, to jump to there. Which one's going to be the second quadrant, and why?
Left because it's in accordance with the right hand spiral.
Swirl, right? If we're going to do it, it's either going to be 1, 2, 3, 4 clockwise, or it's going to be 1, 2, 3, 4 counterclockwise. And which one is the right-handed way? Counterclockwise. 1, 2, 3, 4. All right, so that's all that we have for today. I hope you have a wonderful Wednesday.